here we go. We are going to finish off the semester. This is the last lesson of the semester, okay? We have 3 days of midterm review after our final semester test. After this test, we only have 4 more units of material to get through. Okay, so we're getting there. But to finish off this semester, finish off a semester of derivatives, we're going to change gears when we come back from Christmas break. I want you to have this lesson ingrained in your brain, okay? And it's something that we've already kind of done already. There's a little bit of a difference. But if there's anything you take away from this class at the end of the year and moving forward, is that you know how to find maxes and mins of things using calculus. How do you know how to find maxes and mins of things? What do you do to find maxes and mins of things using calculus? Take the derivative and set it equal to 0. That's it. That's the key. That's the one thing you're taking away from this class this semester. Finding max mins. Take the derivative, set it equal to 0. Okay? Or see when it's undefined, we'll just set 0. Okay? We've done this before. Unit 4 was all about maxes and mins of things. Push phone all the way away. Just call it out. Put your phone all the way away. We've already done this. If I asked you to find the relative max, relative extrema, relative maxes and mins, remember extrema, just another word for maxes and mins. You would take the derivative. Set it equal to 0. Factor to solve. You get 0 and 2. If we wanted to look at the concavity, when we have points of inflections, we'd look at the second derivative, but for right now, just maxes and mins. Take the derivative, set it equal to 0. We'll do our sign analysis of f prime. This is f prime. When is f prime positive or negative? Well, we have f prime when it's 0. We just use some test points because zeros will separate positive and negative values. So plug in something like 3. Positive times a positive is a positive. Something like 1, we get negative. Something like -1, we'll get a positive. Negative times a negative. Okay, it's very important, the interpretation of this. This is f prime signs. This is not, oh, f is decreasing from 0 to 2 because f prime is decreasing. Okay? Or you don't say, oh, from 0 to 2 we're decreasing because f prime is decreasing. No, f prime is negative, which means f is decreasing. From left to right, it's going down. F prime is positive, which means f is going up from left to right. F prime is positive. F is going up from left to right. Do you need a packet of notes? I have extras. Now, from here, we kind of have a general understanding of what it looks like. We could do a little bit more analysis and plug in 0. And say, oh, I have the point 0.05. Great. I could plug in 2. 8 minus 12, -4, plus 5 is 1. So, you know you're going to go up. You go down. You go back up. Okay? Relative max, relative min. Well, the only difference about today is that we are going to focus on absolute maxes and absolute mins. These are called absolute extrema. And absolute extrema means overall maxes and mins. And here we got 2 functions. Looking at the overall function. When does this function have an absolute max or min? Well, in this situation, we can see this is our lowest value. This would be considered our absolute min. And we see up here, this is our absolute max. They happen to be at locations of relative maxes and mins. So it is an absolute min, but it's like a relative slash absolute min. This is an absolute max, but it's a relative slash absolute max.
Damages? Questions if you're like finding maximum.
Yep. Yep. For the other situation, we do have a relative max here and a relative min here. But you can see our function goes up towards infinity and down towards negative infinity. So there's no definitive absolute max or no absolute min. Okay? Other situations where you might not have an absolute max or an absolute min. A quadratic will either have an absolute max or an absolute min, but it won't have both. Okay? Quadratic has an absolute min, but it doesn't have an absolute max. When we have asymptotes, let's say, 1 over x, when x is greater than 0, we are approaching 0, but we never get there. Okay, we're going up towards infinity. This would neither have an absolute max nor an absolute. Okay, so there's some situations where it's like, man, I have an absolute max or I don't. Instead of looking at just overall graphs, we are going to stick to finding absolute extrema on a closed interval. Because we'll notice something when we find absolute extrema on a closed interval. Okay? Closed interval means we'll include some values. Let's take -2 to 3. Okay, so I'm going to just kind of say, let's go -2 to 3. Well, we can see that at x equals -1, that would be considered the absolute max on the interval, even though this function does not have an absolute max overall. You look at it, you say, nope, it's not. It's going up, and it's going down. Doesn't have an absolute max overall, but between -2 and 3, x equals -1 is an absolute max. And then at 2, x equals 2 would be our absolute min. Okay, look at another interval, like -2 to 1. Well, again, we can see that at -1, we have an absolute max. Do we have an absolute min, or is it another situation where we don't have an absolute min? We actually do. It's at 1. Why, Mr. Barker? It's the lowest point. Since we are including the endpoints, this is a point down here. This is a point up here. Well, this is the lowest value at 1. This is what we call an endpoint. Let's look at one more interval from 0 to 2. Well, in this case, 0 is the absolute max, and 2 is the absolute min. I don't have, a hump. I don't have a relative max in between those values, so both of the endpoints are maxes and mins. Okay? What we just showed here is a demonstration of the extreme value theorem. The extreme value theorem states that functions are guaranteed to have maxes and mins, absolute maxes and mins, on a closed interval. Where are those possible locations of maxes and mins? They're consistent with all of our three situations we looked at. Absolute maxes and mins on a closed interval are either where? Endpoints or relative maxes and mins. Okay? That's the extreme value theorem. All right? Let's go ahead and find some absolute extrema out there. We'll come back to this. Let's find the absolute extrema of the function between 1 and 4. Get rid of 3. I think in your notes it says 3. Change it to 1 and 4. We'll fill in the part up top right after this. Okay. Well, absolute extrema will occur either at the locations of relative extrema or at endpoints. Let's just find the relative extrema. F prime equals 3x squared minus 6x. We already did this. Set it equal to 0. 3x, x minus 2. I get 0 and 2. Now, since I have this interval from 1 to 4, on my number line, I'm not going to include 0. I'm literally saying, hey, we're just focusing on 1, and we're focusing on 4 as our start and our end. And 2 was an interesting point. All right, well, we could do our number line analysis again. Between 2 and 4, I could plug in 3, positive, positive, positive. If I plug in a half, or 1 and a half, I'd get a positive and a negative, so that's negative. Okay, what is one thing through this analysis I can definitively say about my absolute extrema? Discuss with your neighbors. Okay, the one thing we could say is that we know we have an absolute min at x equals 2. I know that for certain because my function starts at some value at 1, we go down till we get to 2, and then we go up from 2 to 4. So that means that has to be the lowest value. Okay, so this type of analysis that we've already done can help us determine if we have absolute maxes or mins. But do we know if x equals 1 or is x equals 4 the absolute max? That's what we're going to do. A lot of people think that, oh, it's got to be at 4 because like between 1 and 2, that's less distance than 2 and 4. But all we know is that we're going up and going down. We don't know how quickly we're going up or going down. So I could decrease significantly between 1 and 2 Let's pretend this moved over here. I could go from 1 to 2 here, and then from 2 to 4, I increase a little bit less. So boom, there's my absolute max. So I have my absolute min here, but that's there. Or, again, I could decrease a little bit and increase more. How are you going to tell, Mr. Kaliao, which one is the absolute max? Whichever one has a bigger value. We could tell whether 1 wins or 4 wins because I could plug 1 and 4 into this function. That, my friends, is called the candidates test. That's how we're going to determine absolute extrema on our interval. If after doing the number line analysis, or we could actually just do it and skip the number line analysis. Plug it in. And just compare their, I don't want to say y, because we're not going to just talk about functions. We could talk about max derivatives. We could talk about max positions, minimum positions, max velocities. But compare their values. So f of 1 is a possible max. Sorry, why did I say this is an absolute max? You guys didn't catch me. It's an absolute min. F of 4 is a possible max. Why don't we just go ahead and throw an f of 2 just because we're already here, and we'll confirm that that's the location of the absolute min. Okay? Plug in 1. 1 minus 3 plus 5. Negative 2 plus 5 is 3. Plug in 2. 8 minus 12. Negative 4 plus 5, that's 1. 3 is less than 1. Okay. I plug in 4. I get 64 minus 16 times 3, 48. So 64 is 16 plus 5, 21. Beautiful. Okay, so we have this situation right here, where we decrease less and then increase more. X equals 2 to the absolute min. X equals 4 is the location of our absolute max. Now they may ask you, find the absolute extrema or find the values of the absolute extrema. That means you would be looking for these y values, and you would answer like 21 is my absolute max, or 1 is the absolute min. Okay? Now, let's say they ask you about an absolute max or min, and there's no interval given. So I could ask the same question and just like specify, find the absolute mins of the function. Well, and then I don't include, I would just use a different function. But if you are not given an interval, just do your number line analysis. And typically, if they don't give you an interval, it's because there's only one location where there is a max or min. Okay, so do your derivative sign analysis. Yes. In this case, so, right, good. So let's say I have a derivative that goes from a positive to a negative. I know for certain this is not only a relative max, this is an absolute max. If that's the only sign change, and I'm going all the way to negative infinity and positive infinity. Okay, does that make sense? Okay. So if there's only one sign change, we know that at that sign change, we definitely have either a max or a min.
Once you I don't know how to close it or what to do to check the R value.
Great point. If we had a situation like this, let's just throw some values on 0, 1, 2, 3. And let's say I want positive, negative, positive. Okay, this is the sign change of f prime. Which ones could be maxes? 1 and 3, right? Because I know from 0 to 1, f is going up. And then from 1 to 2, f is going down. So 2 is not going to be bigger than 1, I know that. But from 2 to 3, I'm going up. So the maxes, either 1 or 3. Mins, I start at 0, I go up to 1, I go down to 2, I go back up to 3. The mins will be at 0 or 2. Okay? And depending on the question that they ask you for, like the mins, at least doing this analysis reduces the amount of work that I have to do, and I just need to check, oh, plug in 0, plug in 2. Okay? To find the absolute. All right, let's do some problems dealing with finding absolute maxes and mins. We have a position function. One is the particle furthest to the left on the interval from 0 to 2. Okay, let's talk about position. Okay, this is x of t. If I plug in a value into this, I get a position. So if I plug in 0, I'm going to get a position of 2. So let's say this is 0, and this is my particle. At 0, we start at position 2. Now, this particle can move right or left, right? I want to figure out when it's furthest to the left. Now, it might be a negative value furthest to the left. Maybe 2 is when I'm furthest to the left, and I'm just moved to the right. Maybe I move to the left, and then I move to the right. So furthest left doesn't necessarily mean we have a negative value. It just means we're at a what? A min, right? Furthest left would be a min of position. This is very, very important to understand and think about. It's kind of translating the question, something that seems like, oh, I have no idea. But you could say, oh, I'm trying to find a min position. Whenever this value is the smallest, I'm furthest left. Well, again, finding mins, but now it's an absolute min. We'll take our derivative, set it equal to 0, and we'll do a sign analysis. Okay, now notice our interval's from 0 to 2, so man, I shouldn't have started here. I should have just like started here. And then I'll end here. This is important when we're doing absolute maxes and mins. Know where to start and end. It'll help you. Okay? Now let's see, if I plug in something like 1.5, this is a positive. If I plug in something like 0.5, this is a negative. This is x prime. Okay, this is its derivative. Is it velocity? Yes. So we can think about this in terms of velocity. Our velocity is negative, then positive. When velocity is negative, that means I'm moving to the left, and then I'm moving to the right. So it turns out I do start at 0, 2, but then I move to the left, and then I move to the right. And maybe I move to the left all the way there to the right. Do I have to do any more analysis to determine where I have an absolute min, or when I'm furthest left? Well, I'm done. I know that this must be my absolute min. I did it. Let's figure out the position at that time. 2 minus 3 is negative 1, plus 2 is 1. So we went from 2 down to 1, then back up. Now, what if I asked you, when are we furthest to the right? You determine, when are we furthest to the right? You tell me. Is that 2? Okay. Why is it at 2? What's the y value at 0? Yeah, what's the y value at 2? 6. 16 minus 12. Is it 8? No. Plus 2. Yep. Mental math, man. Okay, so furthest to the right would be at 2. And that's at an endpoint. Okay, different question. Same situation as above, giving you a position function. Now I'm asking you, when is the particle moving fastest to the right? Okay? So, discuss with your neighbors, what would you have to analyze to determine when we're moving fastest to the right? If you go straight to the word acceleration, you're missing the key step, which is like fastest to the right. It means I'm looking for the blank of blank. Fastest to the right would mean my velocity is positive, right? But what kind of value tells me that I am moving fastest to the right? I mean, yeah, you're getting there, but I want you guys to say the max of velocity. You guys are already going that extra step, but like, that's important. When am I moving fastest to the right? When my velocity is at a max. Now, you're going straight there, and you're like, oh, it's when the derivative changes sign from positive to negative. That might be a max. What if my derivative doesn't change sign? I don't know. This is where we just like start here. We're like, velocity is a max. Velocity's max could occur at an endpoint or somewhere in between this 0 and 2, the endpoints. How do I determine the max of velocity? The derivative of velocity, okay? Velocity is a max when velocity's derivative equals 0 or at an endpoint. Now, I already know what v is. We'll start by writing that down. X prime, the first derivative of position, is velocity. That was 6t squared minus 6. X double prime, which is v prime, is 12t. Sorry, 6t squared minus 6t. 12t minus 6. Now notice I didn't even write a because I don't want to think about acceleration because sometimes it'll confuse me. I'm just thinking about the derivative of velocity. I set this equal to 0. I get t is equal to 1/2. Okay. Seems to be that's my answer, right? Let's see. It's not a line. I'm starting at 0. I'm going to 2. I'm looking at v prime. V prime is telling me whether v is going up or going down. Focusing my attention at 1/2. Plug in a value like 1. 12t minus 6, that's a positive. Plug in a value like 1/4, that's a negative. Are we moving fastest to the right at 1/2? No, this is the location of the minimum. This means I might be moving left at this time, or I might be moving to the right, but I'm moving to the right at a slower value than I was moving to the right at 0. And I'm definitely moving at a slower rate to the right at 1/2 than I'm moving at 2. So this is the location of a min. This is not my answer. The possible maxes must be at 0 and 2. So I will go and see, what is the velocity at 0? What is the velocity at 2? The velocity of 0 is 0. The velocity at 2, 24 minus 12, is 12. The velocity at 1/2, just to double check, is negative 1.5. So it turns out I'm not moving to the right at negative 1/2. I was moving to the left, and I'm moving fastest left at 1/2. I'm moving fastest right at 12. This is our max. It's an endpoint. See how there's that extra little bit of details? We can't just assume it's at the location of a relative max. Okay. Another type of max-min thing. You got two functions, 9 minus x squared and x squared minus 8x. So 9 minus x squared kind of looks like this. I'm going to be exaggerated. X squared minus 8x is going to have a 0 at 0. And if I wanted to, I could kind of see where they intersected, but whatever. Let's say it looks like that. Okay? So this is f and this is g. They have a vertical distance between them at each x value. So this is a distance. This is a distance. When is the vertical distance between the two functions the greatest on the interval from 0 to 4? Well, first thing we need to do is find an expression for this blue line. What would determine the distance between those two functions at any given point? The y values, right? So if this was a y value of 3 and this is a y value of negative 4, what's the distance? 7, right? And what do I do to the y values to get that 7? Absolute value of 2 added works, but only for this situation. If it was like 3 and 2, what do I do to these two numbers to get 7? The difference. 3 minus negative 4. Now, if this point was 3 and this point was 1, 3 minus 1, 2. Right? Absolute value wouldn't work there if you added them. Okay, so we subtract them. Now, would that work here at this point? If this was 5 and this was negative 1, you just subtract them, right? So it's at any point we subtract the y values. Well, that means we would subtract the values of f from the values of g from the values of f. That's the distance for a specific x value. So I'd say that the distance is 9 minus x squared minus x squared minus 8x. Okay. Why don't we just simplify that? 9 plus 8x minus 2x squared. We have an expression for the distance. This is important. This is an expression for the distance. How do you find when the distance is a max or a min? We should be definitively all in chorus, in harmony, stating the answer to this. How do we find when something is a max or a min? Take the derivative, set it equal to 0. I've heard better from other classes. Take the derivative, set it equal to 0. Now you're probably thinking, oh, what's going on over here? It doesn't matter. D prime, whatever. 8 minus 4x, set it equal to 0. X is 2. Check. Between 0 and 4 at 2. Let's see. 1 positive, 3 negative. D prime changes from positive to negative. This must be the location of our max when x is 2. Let's go ahead and look at that. Nine minus x squared. X squared minus 8x. Between 0 and 4, let's kind of shift my window down. Wrong one. Okay, so 0 and 4, we can see the distance between these two kind of increases and then starts to decrease. Where exactly does it increase and then start to decrease? It increases until I get to 2. This is going to be our max. The distance is increasing, its derivative is positive. Then this distance decreases until 4. They don't intersect until after 4. But does that make sense? D prime is positive. D, the distance is increasing. Then the distance is decreasing. We found the location where the two are furthest apart. Another distance question. It's a great question. This is a Calculus 1 college type question. Okay? You may not see it on the AP test, but I like it so much to make sure that we do it here in AP Calculus. We got the square root of x and the point 40. 40 is not on the graph of the square root of x, am I correct? Square root of x looks like this, and 40 is right here. Follow me so far? Okay. I want to figure out which point on the graph of the square root of x is this distance the smallest. Could be at an endpoint over here at 0. It's probably not going to be at the other endpoint, infinity. It's got to be probably somewhere between. So I want to figure out when this distance is a min. Well, just like I had in the last situation, I need a formula for the distance between my point here at 40 and a point on the graph of root x. Yeah. We're going to have to do a hypotenuse thing. It's a great idea. So I got a right triangle, which we can kind of see right there. Okay. Now, here's the tricky part. And this is the part that you got to really focus on. What would be considered a random point on this function f of x equals root x? An expression that can signify any point on that function. A lot of people are like, oh, just like some xy. It's like, no, it's not just a random xy. It's a specific y given our x. Oh, because I want any point. I don't know which point. I don't know that it's 4, 2. I don't know it's 4, 2. Could be a different point. So I'm just like an expression for just a random point. What's that? No? X square root x. A point on this function, a random point on this function, is x root x. Okay? And now we are going to create a formula for the distance between any point on this function and this point here at 4, 0. Okay? Now what do? I have to find this distance. What is this distance here between, our vertical and the point 4, 0? These are x values. 4 plus x, 4 minus x. Okay? All right, so that is 4 minus x, the way that I drew it. Now, what would be this distance here? Square root x, or square root x minus 0. All right. Well, if the distance squared is the x distance squared plus the y distance squared, I can replace this x distance squared as 4 minus x squared. I can replace the y squared with root x minus 0. Now, what's an interesting thing is that 4 minus x being squared, is that going to be the same as x minus 4 squared? Think about it. 4 minus x squared and x minus 4 squared. You could even do the math, like x minus 4 squared, x squared minus 8x plus 16, right? 4 minus x squared, 16 minus 8x plus x squared. So they're the same, right? No matter how you do it. So if you'd like, you can write it as x minus 4 squared plus root x minus 0 squared. And if you wanted to, you could take the square root. And what you will discover is the distance formula, which you've probably seen in geometry, in other math classes. The distance formula just comes from the Pythagorean theorem. It's just the square root of the change in your x's squared plus the change in your y squared. Change in your x's give you your x distance. Change in your y's gives you your y distance. Okay? However, I will tell you that finding the minimum distance is the same. You'll get the same answer as finding the minimum distance squared. I'm going to want to use a distance squared formula instead of a distance formula, so I don't have to worry about that pesky square root. Because to find a minimum distance, what would we have to do to a distance formula? You'd have to take the derivative. Do you want to take a derivative of this with the big square root, or do you want to take the derivative of this without it? Okay, we're going to take the derivative without it. So, before I take the derivative, I'm going to simplify it a little bit. I get x squared minus 8x plus 16. I get x squared minus 7x plus 16. I am ready to find the min. Tell your neighbor, how are you going to find the min of that? Take the derivative and set it equal to 0. Okay, take the derivative. It doesn't matter what you have on the left side. You're like, is this 2d? dx? Don't worry about it. In this case, it's d squared prime. It's the derivative of it. We get 2x minus 7, set that equal to 0. I get x equals 7 halves. 3.5. So, turns out, if you're looking at the graph of the square root of x we're going to go from 0 to 5 and from 0 to 3. Here's the graph of the square root of x. Here's the point 4, 0. The point here at 3.5. Right here. That point is the closest to that point. Any other point on the graph of square root x is further than that. Isn't that pretty cool? I think it's pretty cool. Your turn. We have the graph x squared. We have a point 2.5, which is definitely not on the graph of x squared. I want to know which point on the graph of x squared is the point 2.5 closest to that function. We will be using the distance squared formula. The difference of your x's squared plus the difference of your y's squared. What's really important is labeling what a random point on the graph of y equals x squared as. It's not an xy. It's what? X squared. All right, now plug those points into the distance formula. We'll take the derivative and we'll go from there. Go ahead, do it. None. We have x squared. We need to use x squared. And x. My x's are x and 2. My y's are x squared and a half. Oh, this is going to be annoying. Should have picked a different one. Well, instead of foiling everything out, I'm going to just take the derivative using the chain rule. See if it looks nicer. Let's see. I can make this work. No, I can't. That's a 4. Gosh. Well, since I'm multiplying by the 2, it actually does. It's not that bad. So I got 2x minus 4 plus 2x squared minus 1 times 2x. This is after taking the derivative. Then I get 2x minus 4 plus 4x cubed minus 2x equals 0. The 2x minus the 2x goes away. Oh yeah, this was all set up for a reason. I get minus 4 plus 4x cubed equals 0. I get x cubed is equal to 1. I get x equals 1. So it turns out 2 1/2 is closest to the point, 1 1. Isn't that funny how they do that? But wait, there's more. Calculus helps us quickly and easily answer seemingly very difficult problems where we want to find a largest or smallest value, quantity. Example, building a house to have a certain amount of space but with the least amount of material. Finding a route that will minimize the distance traveled. All things we are going to do. Here's an easy example, simple example. It says steps to solve, but don't worry, you'll see. I'll fill in some steps to solve. Okay? We want to find two positive numbers, x, y, where x times y equals 192 and x plus 3y is the minimum. Now, probably before today, and probably for some of you after today, your first attempt would be to just start writing down values that multiply to get 192, and you're like, all right, I got this, Mr. Master. 1 and 192. That's the first one. I'm going to go with that one. 2 and, I need my calculator. Okay, and you would just start listing them off, and then you would start doing the x plus 3y, and you'd see which one would figure it out. But you're missing a lot, because you're missing all the decimal values in between, right? So it's like, man, you're going to take forever. But no, calculus is going to help you, okay? Now here's your key. Here are some steps to solve. You are going to understand that something is fixed, just like related rates. This must be true between our two values. The x and the y must multiply to get 192. I'm going to minimize this sum. I'm going to call it s equals x plus 3y. Now, how do I find the minimum of something? Take the derivative first, Mr. Barker, then set it equal to 0. Don't forget the key step of taking the derivative and set it equal to 0. So my goal is to take s, take the derivative of s, and I don't care what just take the derivative of s and set it equal to 0. But hold on. I got a bunch of variables. Don't I want to make this easier? What did I do in the related rates problems? Take your fixed thing, solve for a value, plug it in. That's what we're going to do. Let's solve for x. Why? Because it just has one extra thing. 192 over y. Let's go ahead and, before taking this derivative, plug this as 192 over y. Okay? Now let's take the derivative. I'm going to say s prime equals 192 over y. That's 192 y to the negative first. Take the derivative, negative 192 y to the negative second. So that's negative 192 over y squared plus 3. What do I do with this derivative, Mr. Barker? I set it equal to 0. I'll subtract 3. I'll multiply by y squared. I get negative 192 equals 3y squared. Negative 3y squared. I divide by negative 3. And lo and behold, I get 64. I take the square root of both sides, and I get 8, because I'm just looking for positive numbers. Which means, without having to figure out any ordered pairs, if I plug in 8 into x times y equals 192, I find x is 24. 192 divided by 8 ends up being 24. I find that when x is 24 and when y is 8, these two numbers will multiply to get 192, and compared to any other pair of two numbers that multiply to get 192, the first number plus 3 times the second number will be the smallest that you can get. Okay? Using calculus, not using guess and check. Pretty cool.
You can't write this.
No, you'd have to literally do like a table of x, y's, and then a table of x plus 3y's. And you'd have to look at that table. Yes, Miss Lee? That's a great question. Because we're not looking really at tangent and slopes. We're just looking at optimizing things. And when we look at optimizing things, we really are going to just change the derivative to be whatever variable we're using. So I'm actually taking the derivative with respect to y in this situation. It's a great question. It's like I'm taking the derivative of y. I've always had dy dx. But in this case, I'm just trying to find a maximum y. Not trying to find a maximum dy dx. Not trying to find a tangent slope, which is dy dx. Instead, just maximizing. Derivatives equal to 0. In this case, derivative with respect to y. It's a good question. Throw that in the next lesson. All right, situation number 2. Now, the two numbers have to add to get 100 if you take the first number and add twice the second number. I want to figure out which two of these numbers produce a maximum when you multiply them together. Understand what is fixed. Understand what you're trying to maximize. We're eventually going to take the derivative of this right guy, this product, and set it equal to 0. But before we do that, let's remove a variable. Probably the easiest one to solve for is x in this situation, again. Instead of using the product rule, why don't we just write the distributed form? In this situation, I'm going to take the derivative with respect to y to find a max y. Get p prime equals 100 minus 4y. Things always end up working out like squares with these problems. Square will have the smallest perimeter. Square will have the maximum area, kind of stuff like that. We can kind of see 25 times 2 is 50. Those end up being the same values. So we have some word problems. More word problems. They're not as hard as related rates, these optimizing word problems. Okay? Gardner wants to make a rectangular enclosure using a wall of a barn on one side and using 120 meters of fencing on the other 3 sides. Find the dimensions that give the largest area. Let's first kind of understand the situation. We got a barn and we got fence. Okay. The fencing. It's a rectangular enclosure. We got an X and a Y. We got 120 meters of fencing. Write down the equation that you can use that says we have 120 meters of fencing. Two X just plus 1Y is 120. Because I got barn for one of the sides. I want to maximize the area. The area is xy. I want to find the max of that guy. Well, in this case, this is fixed over here on the right. This is what I'm trying to optimize over there on the left. Let's solve for a variable. Substitute it in. Take the derivative, set it equal to 0. In this case, I'll take this derivative with respect to x. Find dA dx, and if you think about it, dA dx, the change in my area with respect to a change in x. I want to figure out when that changes from like positives to negatives, because I want the change in area to be the greatest, or I want the area to be the greatest, which means the change in area goes from positive to negative, which means the area is going from increasing to decreasing. A lot of just talk for, take the derivative, set it equal to 0, you'll find the max. Again, we see that kind of square situation going on. It ends up not being a square, but like 2 times 30 gives us 60. Okay. Here we go. My favorite problem. Nope. Second favorite problem. Favorite problem's on the bottom. Manufacturer wants to design an open box. Let's draw a box. Open. There you go. Open box. It's got a square base. Got a surface area of 108 square inches. What is the maximum possible volume of the box? Please write down your two equations. One that you are going to have as a fixed equation, and one that you are going to optimize, that you are going to try to take the derivative of and set equal to 0. I don't know if that helps. We got an open box. X squared y, that's the volume. We get that? Surface area, who's got it? What do you got? Close. It's an open box. So, since it's an open box, it doesn't have a top. Yes, it's just 1x squared plus 4 of our xy's. Thank you, Mr. Wynn. Equals 108. Oh, yeah. Forgot this one's tricky. I want to use this to plug in here. What should I do? What do you got? What do we got? Could factor out an x. Just solve for y is what I'm saying. Thanks, Mr. Holmertz. Watch what happens here. This is great. Okay. We get v equals x squared times 108 minus x squared over 4x. Multiply in this x squared. Boom. 1 cancels. And I get 108 over 4x minus x cubed over 4. All right, I'm ready. Take the derivative. V prime, 108 over 4. What is that? Is that a number? It's 27. Is that right? All right. So we get 27 equals 27 minus 3/4 x squared equals 0. Subtract 27. Multiply by 4. Divide by -3. $36. Gosh, so good at these problems, whoever designs them. That means x is 6. Plug x is 6 back in here. You'll find y is probably 6 as well. But I actually don't know that. So 108 minus 36 divided by 24. 3. Y is 3. All right, final problem. We almost did it. An open box of maximum volume is to be made from a square piece of material 36 inches on a side. This problem will be on your test, and it will be on your quiz. So here's my square piece of material, 36 inches on each side. You're cutting equal squares from the corners and turning up the sides. So I'm going to like cut out a square here and cut out a square here. And then I'm going to kind of crease right here and flip it up. And that's the side of a box. So again, yeah, open on the top. I'm going to cut out a box here, flip this up, flip this up, cut out a box here. Okay. And we can see the base of my box is right here. And these are the sides. Follow me so far? All right. These corners are a variable distance, variable length. But they're squares, so I'm cutting out an x by x box for each of them. I want to maximize the volume. Volume, length times width times height. This would be like the length. This would be the width. And this would be the height. You kind of see how that works because you're flipping things up? What would be an expression for the length? Beautiful. 36 minus 2x. What's the expression for the width? 36 minus 2x. What's the expression for the height? X. Okay. Now, we could distribute this if we wanted to. But I'll show you that if we actually use the product rule here, the derivative is going to be easy to work with. I get v prime equals product rule. Here we go. Derivative of the first piece, I got to use the chain rule, times the second, plus the derivative of the second piece times the first. With me so far? Don't distribute. Don't distribute. Took the derivative, don't distribute. What should I do instead of distributing? Because I want to set this equal to 0. I want to solve. I want a product. What can I do? Pull out of 36 minus 2x. It's the same as when we were simplifying derivatives back in the day. Pull out of 36 minus 2x, and I get negative 4x plus 36 minus 2x. That gives me 36 minus 2x times negative 6x plus 36. Giving me two solutions, 6 and 18. Both of them must be correct, I guess, huh? Let's do some thinking. Are my answers both 6 and 18? If I cut out squares of 18 by 18, I essentially have no box. Another way you could see this is look at v prime between 6 and then ending at 18. If I plugged in something like 1, positive, 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 if I plugged in something like 7, this would be a positive, this would be a negative. So my volume is increasing until I get to 6. My volume decreases until I don't have a box. So this is the size of the squares of the box that I need to cut. All right, good job, guys.